Glowing green bacteria in a laboratory in Amsterdam. Superheated gas escaping from volcanic rock in Iceland. Two experiments both exploring an innovative idea that could help counter the effects of climate change. TechKnow explores the science of capturing carbon. This is TechKnow, a show about innovations that can change lives. We're going to explore the intersection of hardware and humanity, and we're doing it in a unique way. This is a show about science by scientists. Fossil fuels powering the modern industrial economy, but with global economic growth comes global increases in levels of greenhouse gas. Since the 1950s, the US space agency NASA has been monitoring carbon dioxide levels in the Earth's atmosphere. In 2013, climate history is made at the Mauna Loa monitoring station in Hawaii.
On the 9th of May, we measured CO2 at Mauna Loa Observatory in Hawaii to go over 400 ppm, which is a milestone, you could say. We think this is a significant milestone. It reminds us of the fact that CO2 in the atmosphere currently is higher than it has been in the last at least 2 million years. What is also significant is that the rate of increase is rapid.
This computer-generated image shows the flow of CO2 across the globe. The intense red swirls indicate increased burning of fossil fuels during the fall and winter of 2006, which in turn generates higher levels of CO2 over North America, Europe, and Asia. Scientists at NASA and around the world have evidence indicating these increased levels of CO2 in Earth's atmosphere are behind rising temperatures, extreme droughts, and extreme storms associated with global warming and climate change. The prime driver, scientists say, carbon dioxide, or CO2, a colourless, odourless gas. Nature can provide a path for carbon capture through photosynthesis. Trees and plants soak up CO2, but CO2 production has outpaced the growth of the forests. Global temperatures continue to climb higher. February 2017 was the second warmest February ever recorded. One way to stop rising CO2 levels is to reduce dangerous emissions. But researchers are taking another path, looking to science to come up with methods to capture CO2 through innovation. One experimental plan would inject carbon emissions underground, where it could be turned into stone and stored indefinitely.
Welcome to TechKnow. I'm Dr. Shini Somara, standing in a steam plume in Iceland. The landscapes here are absolutely stunning. But Iceland's beauty isn't just on the surface. There's a lot more happening down below.
Iceland, one of the most geologically active areas on Earth. According to Iceland's National Energy Authority, the tiny island nation is packed with more than 200 active volcanoes. But even when they aren't erupting, in Iceland's many volcanic zones, molten magma flows just under the Earth's surface. And that results in a landscape covered with bubbling hotspots and open gas vents. In the middle of one of these hotspots, the Helliseiði power plant, fueled entirely by the energy from the ground below. The geothermal power generated here provides more than enough energy to light and heat Iceland's capital city of Reykjavik.
So we're right on the edge of a volcanic area, aren't we? How important is that for this site?
We wouldn't have the power plant located here if it weren't for the volcano, because where the volcano is, that's where we have the geothermal activity.
Ede Eradottir is a chemical engineer and researcher for Reykjavik Energy.
Yeah, we need to wear the visibility vests and the hard hats.
She took us to the top edge of the volcano to get a close-up view of an active drill station. This is the geothermal version of an oil rig.
Ah. Lovely and warm in here. Oh.
Lovely and warm, yeah. The temperature of the fluid when it comes up is more than 200 degrees, even closer to 300, so we can really feel the heat.
200 to 300 degrees?
Mm-hmm. Yeah.
And so have you drilled down into a crack in the ground, basically?
Yeah, basically we drill into cracks in the ground where we have hot water or just regular water circulating through hot bedrock, and that's how we harness the heat and bring it up to the surface.
Seeing that steam, you can really imagine what's flowing through these pipes.
Yeah, I mean it's much more than that. This is just, the top of the iceberg.
This is incredible, but what's happening here is actually as a result of what's going on thousands of meters beneath my feet. The rock is so hot and porous that when engineers drill into it, they release superheated steam that includes a cocktail of geothermal gases, including CO2.
But scientists here asked, what if those gases, especially CO2, were captured instead of released into the atmosphere? As it turns out, Iceland's largest geothermal plant is also a giant laboratory, home to one of the world's most innovative plans to capture carbon dioxide. Sigurdur Gislason is a research professor at the University of Iceland. He's part of the team behind Carbfix, the carbon capture program at Reykjavik Energy. Even though this is a green energy plant, 0.5% of what comes out of the ground is made up of geothermal gases, carbon dioxide and hydrogen sulfide. The idea is to take those harmful emissions and inject them back into the ground permanently.
Theoretically, you could take all the CO2 that's going to be released in the future, from burning all of known fossil fuel on Earth. You could capture it and you could store it in the oceanic ridges, which are
all of it.
Yeah, all of it. That is 5,000 gigatons of carbon. That's kind of the estimated, emission. If we emit at the current rate increase, causing climate change, causing acidification of the ocean, etc., unless we capture the CO2.
That's incredible that this carbon capture method could be the solution to eliminating our carbon footprint.
Well, it's not a silver bullet. I mean, it's not the solution. It's one of the solutions.
The Carbfix program was conceived in the labs here in 2006. By 2012, it was fully implemented in the field. It takes advantage of something else Iceland's tectonic heritage provides: basaltic rock.
The landscape here is highly dramatic and it's covered in this dark and jagged edge rock, both above and below the surface. It's called basaltic rock and it's formed when volcanic lava cools, and it's perfect for capturing carbon because it's highly reactive with CO2. This is the key ingredient to this whole innovative process, isn't it?
Yeah, this is a chunk of basalt you're looking at. That is the black material, that's the basalt. And then you can see white spots sort of in between. And that is actually the calcium carbonate that we are forming. That's the CO2 trapped.
So these white spots is actually this, isn't it?
Yeah.
Just a chunk of it.
Yeah, this is a very nice calcium carbonate crystal, calcite crystal. And but this is not really representative of what we form within the ground during our injection. That's more like the spots you can see, the basaltic rock here. This process is happening here in Iceland naturally. For example, in our geothermal areas where we have volcanic CO2 interacting with our basalts, turning the CO2 into carbonate minerals. So then we thought, why not test this interesting idea out here in Iceland? I mean, we have our geothermal power plant providing a source of CO2 that can then be captured and injected back into the ground and see if we can utilize and accelerate this natural process.
So the process is happening naturally, but here it's happening at a much faster speed. Did you predict that?
Yeah, so I actually, in the beginning, I was involved with the project as a part of my PhD work. The model predicted mineralization to occur within 5 years' time, but it proved out that the process is even faster than the model predicted because the CO2 was turned into stone within only 2 years.
2 years.
And once the CO2 is turned into stone, you don't have to worry about it. It's not going anywhere. It's just buried in the ground as rock.
The process begins at the production well. Water and superheated steam is sent down these pipes, and into the main power plant below. It's used to turn the plant's giant turbines, which produce electricity.
The steam drives the turbines, generating electricity, and the water is taken through heat exchangers, where it heats up cold water, which is then transported to the city through pipes, and there we use it for showering and heating our homes.
Once the steam has been used, it's usually released back into the atmosphere. For the Carb Fix project, the geothermal gases, about 0.5% of the steam, go to these special cleaning towers. That's where the carbon capture process occurs.
So the gases get a shower. What does that mean?
Yeah, they actually flow through a column where we have water droplets falling down, and the gas stream flows in the opposite direction.
So a gas meets a liquid.
Yeah, and during that sort of interaction, the CO2 and hydrogen sulfide, they dissolve into the water droplets.
That water is sent back down a pipe to this injection hut, several hundred meters from the main plant.
So Etta, this is really the heart of innovation here in this room. What happens?
So here we are actually injecting water containing dissolved CO2 into the ground, into the basaltic host rock, where the chemical reactions take place and turn it into rock.
So the gas has been dissolved in water. Is that what's coming up through this pipe then?
Yeah, here in the pipe we have about 30 liters per second of condensed steam actually containing dissolved CO2 and H2S flowing through here. You can, if you look through the window, you can see that there aren't actually any bubbles visible, even though we have a lot of fluid flowing through it, and that's because all the gases are dissolved.
It's hard to believe that there's actually 30 litres per second of water containing gas flowing through here. It just looks like it's clear.
It looks empty, but if you look closely, you can see sort of very small particles moving around a little bit. So it is actually happening, and you can see it's under pressure, 9.5 bars.
The final step in the process is where the chemical reaction happens. The water is pumped down this large pipe to a depth of 1.5 kilometers. That's where it hits bedrock, and that's where the chemical reaction takes place. As they like to say here, it's where gas is turned to rock.
So what happens after we inject the CO2 is that the CO2 is dissolved in water, which is then acidic, and the acidic water dissolves the basaltic host rock, releasing calcium, magnesium, and iron into the water fluid, where it can react with the CO2 that's already there and form these carbonate minerals.
Basalt reacts fast and forms the rocks. Were we surprised? We have done some experiments and we have done some reactive transport modeling where we predicted that this would take of the order of 5 to 10 years. No one really believed us, and then you really have to do it. And then we injected and we found out that we could mineralize in 2 years, which is a fantastic news.
The plant, already green, has reduced its carbon footprint by 1/3. More importantly, a team of PhD students at the University of Iceland is conducting a new round of testing to figure out why CarbFix is working so well and whether it has global applications.
So this machine here is very much like that small hut on the geothermal power plant site.
Yes, where it's mixing together, so I'm reenacting that here.
What are you trying to find from all this experimentation?
So the main aim is to figure out where the kickoff is. When is the CO2 reacting with the basalt to form carbonates? Like, why is the carbonization so fast? I mean, in other carbon storage methods, it takes tens of thousands of years.
So is this a procedure that could be copied around the world?
That is the hope. I mean, right now it has been done in Iceland, and they are doing studies in the United States in the Columbia River area. We have to try and link up with other companies and universities and other countries in the world in order to bring this method to them, but also alter it to what type of industry they have and what type of rocks they have. And then, in a way, looking at the different industries, seeing what they do on a daily basis and seeing how you can alter it in such a way that they can also store their gas emissions in the ground.
So it's working very well at the geothermal plant, but what are the other applications of this technology?
Well, the other application, of course, we want to get to coal-fired power plants, where the majority of the emission is done. Also, we want to get this to smelters. We need in the future, even if we abandon fossil fuel, we will need iron, we will need aluminium, and we will need cement.
Scientists here say they have a long way to go, but they would begin testing the carb fix process at power plants and smelters situated in coastal regions near ocean basaltic rock. So far, tests at the energy plant show no negative impact on water supplies downstream from the injection site. Other methods of carbon storage rely on burying the gas in geological formations or injecting CO2 into depleted oil wells. The carb fix process is the only one that utilises a process that actually turns the gas into rock.
So how can this be expanded globally, this technology?
Well, basalt is the most abundant rock type on surface of Earth. And we have big plains of basaltic rocks in the States, in India, in Siberia, but also the whole oceanic floor.
Wow, that's a lot of surface of basalt, isn't it?
And one of the downsides of this method is that we need a lot of water because we want to dissolve the CO2 completely before we inject it. If we use seawater and pump it into the oceanic floor somehow, we have endless supply of water and as much basalt as we could imagine. But the question remains how much of this would be practical to use.
Basalt will not be the only way to capture and store. This is the first experiments we do, and that is now applied on an industrial scale. But conventional way of capturing CO2 and compressing it and injecting it to sediment basins, they've been doing it since 1996. So there's a lot of know-how there. What is needed is that we need to put a price on the carbon. There has to be an incentive for the industry to do it, and it should be included in the price of fossil fuel. The price of capturing and storing the carbon. Once we have that, then I'm very optimistic. The know-how is there. Of course, we always have to work on ways to actually lower the price, but it is doable with the present knowledge we have, but it's costly.
In 2015, the US National Academy of Sciences issued a report on geoengineering, the science of using technology to counter the impact of climate change. The panel's conclusions: the benefit of carbon dioxide removal were high and the risk low, but costs posed a challenge. They called for more studies to determine if long-term storage of CO2 could be safe and effective. Scientists at the University of Iceland are hard at work on those studies.
Capturing CO2 is just one possible solution, but scientists in Amsterdam have another plan. They're not burying carbon dioxide, but they are finding another way to use it. For TechKnow, here's Dr. Crystal Dilworth.
Scientists in Amsterdam are studying another solution to help reduce global CO2 levels. They're innovating green manufacturing techniques of some common products, like plastics, that actually remove instead of add carbon dioxide from the atmosphere during production. Currently, the plastic manufacturing process emits huge amounts of carbon dioxide into the environment, adding to the problem of climate change. But what if a new technology could produce a type of biodegradable plastic that could actually help reverse the greenhouse effect? The possibility of this lies in cyanobacteria, an ancient organism that first evolved 3.5 billion years ago, which turns carbon dioxide into valuable organic compounds from which plastics can be made.
There's a whole variety of organisms that still do photosynthesis like plants do, but there is one particular category in these microorganisms that we call the cyanobacteria, and this is an example of that, the blue-green algae.
Here in Amsterdam Science Park, a young startup has grand plans, harnessing the photosynthetic power of cyanobacteria not only to reduce CO2 in the atmosphere, but also to produce Earth-friendly consumer products. The science behind this begins with an understanding of photosynthesis. Plants and some bacteria use energy from the sun along with carbon dioxide and water from the atmosphere to produce oxygen and organic compounds. The oxygen is put back into Earth's atmosphere, and the cycle continues. scientists have found that cyanobacteria, one of the oldest organisms known to man, can be engineered in the lab to excrete commercially valuable molecules.
Although there are differences in climate between various places on Earth, we also find many different cyanobacteria, and in principle you could find for any spot where you would want to apply your technique, you could find a cyanobacterium that is optimally adapted to carry out the process that you have designed.
In this lab, living cyanobacteria conduct photosynthesis under artificial conditions and are engineered to excrete a number of specific compounds used in products ranging from plastics to fragrances to pharmaceuticals. The cyanobacteria excreted compound used in the manufacturing of bioplastics is lactic acid. Dr. Klaus Hellingwerf is a microbiologist spearheading the cyanobacteria research.
And here you see an example of a product that can be made by the cyanobacteria in very large amounts, and in this case this is one of the optically pure forms of lactic acid. And then if you have a culture, a liquid culture, that has been modified to produce the lactic acid, and you let it produce for a while, this lactic acid polymer can then be used to make, well, consumer products of plastic. And there's also a very important product that will become much more important in the years to come, and this is the lactic acid that they used in 3D printing. And my expectation is that the amount of products that we will be using that have been produced in a 3D printer will enormously increase in the upcoming years.
Growing cyanobacteria to make lactic acid for use in plastic manufacturing requires a detailed scientific recipe. Researcher Dr. Sabrina Boten explains how the cyanobacteria is grown in the lab.
Here we grow the pre-cultures that we then use to inoculate large bottles that will be again used to inoculate our pilot facility, which is from 300-400 liters up to 1,000 liters.
So you're growing a small amount in here,
yeah,
and then you'll dump it in what looks like an empty, clear
liquid.
Correct.
Yeah.
And then it grows to be this green.
Yes, exactly, yeah.
What's in here right now? What are these algae
producing? We are
producing?
cultivating lactic acid producing bacteria. What we do is monitor as close as possible all different parameters, from pH to temperature to nutrient concentration, in order to find the best recipe for the medium.
After the lactic acid producing cyanobacteria is engineered here, it will be moved to other labs with larger bioreactors to scale up production, increasing the amount of bioplastics that can be manufactured later.
Normally you don't think about plastic as necessarily being good for the environment, but these are?
Generally there is a problem with plastics that if they are very recalcitrant, that means that once they are deposited in the environment, they will stay in the environment and they will not degrade, or degrade only very, very slowly. And the nice thing of this plastic is that it is based on molecules from living cells, and that means that there are also enzymes in living cells that can break the connection and then can degrade the plastic. The nice thing of this type of polymer is that you can make blends of these polymers that have a rate of degradation that you can set when you make the polymer.
It's tunable.
It is tunable. You would presumably want this beaker to be degraded much faster than the material in this 3D printing.
So you're proposing an almost entirely closed loop. You start with CO2 in the atmosphere, you use the modified cyanobacteria to create a plastic polymer that humans use, goes to the landfill, is broken down and turns back into a carbon-rich gas.
This concept is very important, and we call it the carbon cycle on Earth. And now, the last 200 years, mankind has learned that it is very cheap and attractive to burn all that fossil reserves. However, if we continue to do that, that will create this problem of increased CO2 and global warming. And that's why it is very important to change the carbon cycle into a cycle where all the carbon that is fixed by photosynthesis, either plants for food or these cyanobacteria to make materials, all this fixed carbon is used, and after use, ideally it is reused, and once it is CO2 it can enter the cycle anew, and with the energy of sunlight new products can be made.
Using nature and science to combat climate change, it might just have potential. For TechKnow, I'm Dr. Shini Somara in Iceland. See you next time.